Welcome to class meeting 6 of EECE574, the graduate level probability and random processes. The first announcement is related to the first quiz that will be taken on Tuesday, March 14th in the class meeting hour. So you will have maximum 1 hour, 15 minutes, and it's an open everything quiz, so you can bring even your notebook connected to the internet. Every textbook, every book you can access, even the old homework problems, even some manuals of the textbook. However, you cannot be assisted by any human being live, okay? No interactive thing, impossible. But if you want, you can use ChatGPT, but it will never help. Okay, so you cannot ask your father or mother, okay, or your friend to solve your problem. You can't do that. However, you can look up any web page, any textbook, any material, no problem. Got it? Any question about the quiz? Okay. By the way, I'll be out of town on Tuesday, so one of my RA will proctor the quiz. Homework 4 is assigned already, as you've seen from the PLMS, and homework 5 will also be posted soon, and they are both due on the same time, just before the quiz. Got it? As usual, handouts and annotated handouts are available at the course webpage, and you know the passwords, right? If they are password protected. Lecture videos are continually uploaded to Postec, CISL.Postec YouTube channel. And if you want to contribute, please put clickable timestamps. Corrections, I have one as pointed out by Young Chang. Last time during the class meeting, when I was talking about why the stationarity to order 2 implies the stationarity to order 1, I made a mistake. So we started from what? We started from this property. Okay, they are they are invariant under time translation. Since it's assumed, the random process is assumed stationary to order 2, whether you add some time displacement capital delta, the 2-dimensional or second order PDF of the random process does not change. So from this equality, you integrate with respect to the variable x2 to marginalize and obtain the first order PDF of x1, but last time I used x2, so it was mistake. Should be corrected to the first order PDF of, again, wrong. x1, got it? So we need that 1 delta. So it's stationary to order 1, got it? And other than that, I could not find any corrections. By the way, I need to add some concepts, but I'll be visiting them soon. By the way, we are still talking about chapter 9 of the main textbook. So far, what I have told you is this. How can we characterize a random process? There were 2 methods. First one was based on using the nth order joint probability mass or density or cumulative distribution or characteristic functions. And the other was the measure theoretic approach using an underlying abstract probability space, and we assume a random experiment, and its outcome drives a deterministic mapping rule that is parameterized by time index t and also parameterized by the sample s. And depending on whether t is a natural number, t is an integer, t is a real number, we sometimes call it a sequence of random processes, a discrete time random process, or a continuous time random process. By the way, I especially emphasize that sometimes we need to limit the observation interval of a continuous time random process. So it is not necessary for us to have t always the entire real line. Even though we have a finite interval, we still have uncountably infinite random variables, so it's okay. Second, how can we compute an ensemble average given a random process? The first thing was so-called the computation of the mean path or mean function. And the second one was related to the computation of the correlation function, or if it's obvious, it is not obvious, we say the autocorrelation function of a random process. The notation is using capital R and subscript X and also X. And first argument is the sampling instant of the first random process. Second argument is for the second random process. So we have this notation rewritten as the ensemble average of the product of X of T1 and X of T2. By the way, as we have done for the mean path computation, this expectation may be written as this double integration. So we use the second order PDF of the random process X, and we introduce two variables X1 and X2, and we compute the double expectation. Got it? By the way, as I emphasized, some authors of textbooks or papers love this notation because now our word processors allow subscripts of subscripts. So precisely speaking, this would be preferred, but due to the convention, people more prefer this notation. That sometimes raise some confusion. But anyway, correlation of the random variable capital X of T1 and comma X of T2. So sometimes people use comma here to be picky, but this is okay. By the way, given a random process X of T, we can also define a Pearson correlation function cross or simply the correlation function, correlation coefficient function, which is defined as the covariance function divided by the square root of the covariance function evaluated at T1 and T1, and the square root of the autocovariance function evaluated at T2 and T2. In other words, it can be written as the expectation of the kind of centered and normalized version of X at time 1 and centered and normalized version of X sampled at T2. Got it? And as you know from statistics or undergraduate probability and random processes, the Pearson correlation coefficient for real random variable, two random variables, is always greater than or equal to -1 and less than or equal to +1. By the way, here, sigma sub X of T is a very rare notation, which I love, and that is the kind of standard deviation of the random process that is related to the variance of the random process, and which is what? In terms of the covariance function, This is C sub XX evaluated T1 and T1. Got it? Okay, what else? Yeah, we also covered this notion. Given a single random process, how can we classify this one in terms of stationarity? There are many different definitions of stationarity, like Y-sense stationarity or strict sense stationarity. Some people say strict sense stationarity is defined as the stationary to any finite order n, but some people say that, okay, strict sense stationarity has multiple levels. For stationary to order 1, stationary to order 2, stationary to order n, and strict sense stationarity. So depending on the researcher's preference, they say strict sense stationarity has a very narrow sense or somewhat relaxed sense. But anyway, you need to remember this Venn diagram. So given the set of all random processes, the subset of stationary random processes is very, 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 very small. However, let me exaggerate. So here goes the what? The stationary to order 1. Then inside it, we have the set of stationary random process to order 2, 3, 4, and eventually we have the strict sense, narrow sense, the strict sense stationary random processes. And here goes another subset called the set of Y-sense stationary random processes. Got it? So remember this Venn diagram. Especially these Y-sense stationary random processes are defined only using two moments. First one is the sample path, and the second one is the correlation function or covariance function. Actually, it would be better to say that Y-sense stationary random process has constant mean path, and its covariance function a function of time difference. However, from the covariance function and the mean path, you can uniquely define the correlation function or vice versa, which means that from mean function and the autocorrelation function, you can always uniquely define the covariance function. So any definition is okay. Now, since we covered the classification or some notations, especially the stationarity notion, we wanted to extend those notions to multiple random processes. So the first thing was joint stationarity. Suppose we have two random processes. First, what is the definition of the statement? What is the definition that two random processes are jointly distributed? Which means that we can find any joint PDF or PMF or CDF or characteristic function by taking m samples from one random process. So we have m random variables from X and n random variables from Y. And then we put them together, and we must be able to find the joint CDF, PDF, PMF, or characteristic function. Got it? Now, what is the stationarity of two random processes? Same. So you have just constructed a joint CDF, and that should be invariant under time translation, or it should not change if you choose different time origin. Got it? So joint stationarity is very simple, as we've seen where far above, actually. Where it is? Okay, here, joint stationarity, we've already seen. And then okay, what about independence? So given two random processes, you want to say that two random processes are independent. Then again, you use that Kolmogorov trick. So you choose m random variables from X. You choose n random variables from Y. And then you put a random vector, you form a random vector, you form another random vector. And then you consider the joint CDF, PDF, PMF, or characteristic function of these two random vectors. If this joint CDF factors into each marginal CDFs or PDFs, PMFs, characteristic functions, then they are independent. Got it? So this joint stationarity and independence can be easily extended to from two to multiple, two random processes to any multiple random processes is very easy. Now, related to the independence, we have to remember uncorrelatedness. So some interesting property of independent random variables was this one. Independence implies expectation of the product of two random variables can be factored into the expectation of individual random variable. Why, by the way, is this true, given two independent random variables? And you may say that it's too obvious, but actually it's not. So how do you prove? Yeah, as I just told you, you use the fact that the joint PDF factors. So what you do is that we rewrite this expectation of product by using the joint, for example, PDF. And then independence is equivalent to the factoring of joint density. And then from the calculus, you can separately compute the integration. And they are merely the expectation of Y and the expectation of X. Got it? By the way, given two jointly distributed random variables, sometimes this holds. However, they are not independent. Okay? So independence implies uncorrelatedness. The converse is not always true. Got it? Same thing happens in two random processes. By the way, before we define the uncorrelated random processes, let's try to use that notion of uncorrelated random variables given two random processes. So you have X and Y random processes. Even though I say you are given X, actually how many random variables here in the back? Infinite, right? And here, infinite. Now, suppose you choose some specific X of T1 and you choose specific Y of T2, and they are uncorrelated. However, if you choose other pair, they are not uncorrelated. In that situation, do you want to say that these two random processes are uncorrelated? Of course not. So this simple logic implies that uncorrelatedness of two random processes must be something like this. So you choose arbitrary T1 and T2. And this expectation factors into two expectations. Here, the key is this. For any pair of T1 and T2. Got it? Then you say that two random processes are uncorrelated. Got it? Now, what is the definition of orthogonality given two random variables? And you know that the orthogonality means what? The expectation is 0, right? And the same happens. Two random processes are orthogonal does not mean that specific pair of T1, T2, you have an orthogonality, but you have orthogonality for any pair. Sorry. Okay. So two random processes are orthogonal if and only if for any choice of T1 and T2, the two random variables, x of T1 and y of T2 are orthogonal. Got it? So very straightforward as far as you remember that you have infinite random variables and also another set of infinite random variables. Got it? By the way, uncorrelatedness has something interesting. So same as in random variables, independence implies uncorrelatedness of random processes. So two random processes are independent, implies these two random processes are uncorrelated. However, the converse is definitely not always true. What else do I need to emphasize before I go back to Gaussian random vector and process? Am I done? Oh, yeah, this one is missing. So these two lines mean what? What does this mean? So whenever you see the left-hand side, you need to replace it to the second line, right? Expectation of x and y at T1 and T2. The right side, the expectation of, so what does this mean for all T1, T2? So two random processes are uncorrelated. Now, what is the covariance, cross covariance function between x and y? You can rewrite it by using r sub xy minus mu sub x and mu sub y. So what does this mean? If two random processes x and y are uncorrelated, then its cross covariance function is always 0. Here always means that 0 for all pair of T1 and T2. Got it? And yeah, this part I already mentioned. So we are done. Okay, what else do I need to review? Yeah, Gaussian random vector. So where it is? Yeah, here. So before we talk about Gaussian random process, we need to recall the definition of a random vector and definition of a Gaussian random vector. Unlike most of the textbooks, of course, some textbooks love this characteristic-based definition as I love. I love this notion, definition. So you are given a random vector and its characteristic function, that is, this is the definition of the characteristic function, can be put into the form of an expectation with the exponent given by j. Of course, you know that this part is same as j omega transpose mu x, right? Because in our Fourier transform, we usually state j first and then omega next and then something, right? Anyway, so the first term is related to the j omega and the first order moment of the random vector. And second term is related to the second order moment of the random vector. And this is the quadratic form. Got it? So whenever you can put the characteristic function of a random vector in this form, then it's Gaussian random vector. Got it? And here, the mu is actually nothing but the mean vector of the random vector. And this matrix is nothing but the covariance matrix of the random vector. So this is always positive semi-definite or non-negative definite. Okay. So that means sometimes it's not invertible. Okay. For some Gaussian random vectors, you may have non-invertible covariance matrix. That's why I hate using the density function to define a Gaussian random vector. Anyway, suppose we are lucky to have invertible covariance matrix. Then, in that case, the density function can be written in this nice form. By the way, if the covariance matrix is not invertible, by using a delta function, as we loved and used in our signal gen systems, actually, we can still write down our joint density function, but the mathematicians may not love it, and even some of us may not love it. So I just would restrict to this case. Okay. Then what? This 1 over square root of 2 pi raised to the power of n, and the determinant of this covariance matrix, which is always positive in this case. And then we have another exponential function as we had this, okay? And here we have a quadratic form where the covariance inverse appears, and then x is now centered to the mean vector. Got it? So as you remember in signal gen systems, if we reduce the size of the random vector to 1, then what? A time domain Gaussian pulse is Fourier transformed to a frequency domain Gaussian pulse. Here, Gaussian pulse means that you have e to the negative something times squared of the variable. See that? Here, e to the negative something, right? Something, and square of the variable. Got it? Of course, it is shifted by mu. And again here, e to the, let's drop this. Anyway, this is the constant multiplication if you factor it out. So you have e to the negative something and variable squared. Got it? So the characteristic function and the PDF in statistics and probability, or in signal gen systems, t squared and f squared, okay, is multiplied by some negative number. That may give you a simpler way to memorize. By the way, let me give you a special case of the joint PDF where you have delta function. Suppose you have x follows Gaussian distribution with zero mean and unit variance, and y is also Gaussian, but they are the same. Okay, two random variables are the same. Then what is the joint density of x and y? So actually x and x. Got it? This is special case. What do you think? And whenever you have difficulty in figuring out two random variables case, just recall that the density function is nothing but a mathematical refinement of two-dimensional histogram. Okay, so just imagine you have a random number generator that generates x and y. However, actually, they are wired like this in this case. Got it? Now, you ask that random vector generator to generate a pair of x and y. You observe it, and you put a dot there. Okay? And definitely, they must lie on y equals x line. And then you ask the random vector generator again and again and again to generate the outcomes independent and identically. What will happen? They will distribute on this line, and closer to the origin, you will observe more. So if you project the points to the x-axis, you will have some one-dimensional Gaussian dots. If you project to the y-axis, you will again have one-dimensional dots. But what? What do you guess? Here, square root 2 pi squared, and what? How? So it's complicated, right? But you have some constant times delta of that constant function of x and some delta of x minus y. What does that mean? So this equals some function of x or y if you want, and times delta of x and y. So this is kind of in two-dimensional plane, you have impulse fence. Okay? So you have impulse fence. So when you integrate, it kicks in and reduce the double integral to single integral, and it will give you 1, because whatever, whether it is singular or not, if you have a joint density, that should integrate to unity. Got it? Anyway. So we've seen the definition of a random vector, and I have written down the property. By the way, what is the single most important property of a Gaussian random vector? Anybody? You have to remember this. Any affine transform, you may say linear, any affine transform of a Gaussian random vector generates a Gaussian random vector. Okay. So let's review what is an affine transform. So where it is? I remember I brought some page here. Okay, got it. This is from the chapter 5 of EECE574. So this is the same as we've done. Okay, let's see this one. Even though it lacks of this constant vector v, so it's a linear mapping, right? So you are given a Gaussian random vector x, and this may be length m, or let me say length n. Okay, so by the way, it's an abuse of notation saying that random vector is a member of R2N. Okay, actually, its realization is a member of R2N, right? But I just for brevity, I will say. So x has length n. Let me use capital letter. And y has length m. Got it? Then, in order to make this linear mapping make sense, A must be what? An m by n real valued matrix. Given that, of course, sometimes this m is 1. What does that mean? A matrix is a row vector. So the product of a row vector and column vector gives you a scalar, which means that you now have a random variable. Sometimes x is length 1 scalar, but A is a vector. In the case, you may say that, okay, the entries of y is just scalar multiples of x. That is similar to what we've seen, right? When x equals y, but anyway. So this includes any special cases of just I mentioned. But anyway, so given this linear mapping, now let's show the random variable y is also Gaussian. By the way, adding B is very simple, so it's you do it, okay? Anyway, here, so we start from, again, the characteristic function of y, okay? Why do I do that? Why don't I use the joint density? As I just told you, if x is a random variable, Gaussian random variable, and A is a column vector, in that case, you have a definitely degenerate or singular random vector, which may not have nice form of joint PDF. You must have some impulse fence and which you don't like it, okay? So we use a characteristic function, which is powerful, okay? We don't need any inverse. So we start from the joint characteristic function of y, and let's use variable omega vector. Now, by definition, this is nothing but the expectation of e to the j times omega transpose, and this is y. Y equals ax by definition. Now, this is a trick, okay? Some omega transpose ax equals ax transpose omega, right? And ax transpose, sorry about that. Yeah, you have to transpose it. So just a second. Yeah, let me do this. Okay, so this one, omega transpose a x equals omega transpose a x and a transpose omega transpose x. Got it? So this is the trick. We have omega transpose ax here. Then you put parentheses, no problem. And then this is a row vector, right? This is a column vector. So you transpose this one. So transpose of transpose is that one, right? So a transpose omega transpose x. Then what is this? If you consider this as some other vector, nu, that is what? That is the characteristic function of random vector x evaluated at nu, and nu is a transpose omega. So it becomes the characteristic function of x evaluated at a transpose omega. And we have assumed that x is a Gaussian random vector. And what is the characteristic function of x? You have here, right? Now, instead of omega, put a transpose omega. So here, this becomes a transpose omega, a transpose omega, a transpose omega. Then you can rewrite in this way. Especially, I will kind of fill up this part. So here, let's plug in a transpose omega, and then what? See this part? So you have omega transpose a cxx, and here a transpose omega, and we put parentheses here. So we have omega transpose a cxx, a transpose omega. Then what is this? As I told you, if the characteristic function of a random vector can be put into the form of e to the some j omega something minus 1/2 omega transpose something omega, then it's Gaussian. And so this is our new mean vector. And this is our new covariance matrix. And y is Gaussian. Okay, so defining a Gaussian random vector by using the characteristic function is very, very powerful. If you use the joint density, you will have difficulty. You have to exclude some very interesting cases as a especially graduate student. So I love this. By the way, as I emphasized again and again, you do this yourself, okay? And I'm not saying that it will appear in your quiz, but it's likely, okay? If you take 100 times, it will appear more than 30 times, I guess. By the way, of course, we have a very special case of what? This covariance matrix is a diagonal matrix. Then what happens? If it is a diagonal matrix, this quadratic form is a summation of what? The diagonal entry times omega square, diagonal entry plus next omega square, something like that, right? And from the property of the sum to the power, we can factor the characteristic function. And what does that mean? The independence. Got it? So in Gaussian random vector, if the covariance matrix is a diagonal matrix, then we have independence. Got it? Of course, there we assume what the sigmas are positive, by the way. Okay. So as I repeat again and again, use the characteristic function to clearly think with the Gaussian random something. Now we are ready to go back to the Gaussian random process. So here goes the Gaussian random process section. A continuous time random process. Okay, we can of course define for a discrete time random process. But anyway, so a continuous random process x of t is Gaussian if what? So here you have a bag and saying that random process x of t. How many random variables do you have? In this continuous time case, uncountably infinite. Now you want to say that it's Gaussian. What would it mean? Whatever number n, whatever n tuple t1 up to t sub capital N, you sample, so you collect x of t1, x of t2, dot, 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 up to x of t sub capital N. They are jointly Gaussian. Okay. In that case, we say this random process is Gaussian. Got it? So very simple. Now, in terms of our characteristic function, what would it be? So you take for any n tuple, you put them together and form a random vector. And the characteristic function of this random vector. Of course, some of you may not like my underline to denote a vector, but I really love it, so tolerate it, please. So you have the joint characteristic function of a random vector now, because you already have sampled, and you have length n vector omega, and what? You have a very nice form of a characteristic function, e to the first j omega mean minus 1/2, and you have a quadratic form with the covariance matrix of that random vector. Got it? And here, definitely this one is the expectation of the random vector, and this is the covariance matrix of the random vector. So